Good morning. Welcome to the first lecture on module 4. So in this module, I'm going to discuss about what is infinite series and power series solutions and few concepts based on the infinite series and power series solution. In this lecture, I'm going to discuss about only what is infinite series and how to solve the infinite series. In the next coming lectures, I'm going to discuss briefly about the power series solution. So before learning about infinite series, first we will see what is meant by series. Series is a combination of numbers or variables in an order. So infinite series is nothing but it's a combination of infinite numbers in the order. So in this lecture, I'm going to discuss briefly about how to find the convergence and divergence of the infinite series and also about few tests on infinite series. So first we will define what is infinite series. If un is a function of n defined for all the integral values of n, an expression of the form u1 plus u2 plus u3 plus so on plus un plus so on till infinity. So containing infinite number of terms is called an infinite series. So already I told that so series is a combination. So here I'm taking an infinite number combination. So this type of combinations will be called as an infinite series. Say for example 1 plus 2 plus 3 plus 4 plus 5 and so on plus till infinity is an one best example for infinite series. So the infinite series is usually denoted by summation n from 1 to infinity un, or simply we can call summation un also. So where this un is called nth term or general term of the infinite series. So now I'm going to discuss about what is meant by convergence and what is meant by divergence. So first let me take the series. So a series summation un is said to be convergence. So here I'm going to discuss about the convergence series. So when we call the summation un is convergent is, so if limit n tends to infinity, Sn will be equal to L. Well, and this L is an finite quantity. So if this condition is satisfied means we can call the series is an convergent series. Similarly, I can call the summation un is divergent. When means if the same limit n tends to infinity, Sn will be equal to plus or minus infinity. If I got means we can call that series is an divergence series. So after applying the limit, if I got a finite quantity say L, so we can call that series as a convergent series. For the same series, after applying the limit, if I get plus or minus infinity, we can call those kind of series is a divergent series. So to test the convergence of the positive terms, mainly we have two tests here. The first one is Cauchy's root test and Lemberts ratio test. So in this lecture, I'm going to discuss how to apply Cauchy's root test and Lemberts ratio test. In the next lectures only, I'm going to take the examples related to Cauchy's root test and Lemberts ratio test. So first we will see how to apply the Cauchy's root test. So Cauchy's root test. So if summation un is a series of positive terms. So I'm taking one series here and that series is a series of only positive terms. And now applying the limit n tends to infinity with the nth term of the series un I'm taking here with whole power 1 by n should be finite here. Okay, applying the limit n tends to infinity for the general term of the series un with whole power 1 by n should be equal to L. And here we can call this series is convergent if the value of L is less than 1. So if the value of L is less than 1 means, so obviously we can conclude the summation un is convergent in Cauchy's root test. Similarly, if the same value is greater than 1 we got means, we can conclude that that particular series is an divergent series. Suppose if we got the value of the L will be equal to 1, we can conclude that the Cauchy's root test will be failed here. So while solving the problem, we have to note few points here. So to simplify some standard functions, we have to use these three formulas here. So to simplify, limit n tends to infinity 1 n power 1 by n. So we can read in the problem, we can replace this complete term as directly 1. In the same way, if limit n tends to infinity, 1 plus 1 by n whole power n can be replaced as e, or e can be written in terms of the value also, that is 2.7. Similarly, limit n tends to infinity, 1 plus x by n whole power n can be replaced as e power x. So here we can observe that. So in the second formula, no x term here, so I got only e value. Since here the x term is there, I got the formula like e power x. So in the problems, while solving it, we can utilize these three standard formula for the simplification of the equations. So now we will see what is how to apply D'Alembert's ratio test. So if summation un is a series of positive terms, and if limit n tends to infinity, un plus 1 by un is equal to L, and where L is a finite quantity here also. So then the summation un is convergent if L is less than 1. Similarly, if L is greater than 1, we can conclude the summation un is divergent. In the same way, if L is equal to 1 we got means the test fails. So the condition is same for both the Cauchy's root test and the D'Alembert's ratio test. The only change, only formula. There the formula will be limit n tends to infinity un whole power 1 by n. Here the formula is limit n tends to infinity un plus 1 by n. So the thing is how to identify for the which problem we have to apply Cauchy's root test, and for the which problem we have to apply the D'Alembert's ratio test. So if the problem contains the terms like factorials in the denominator, so easily we can go for the D'Alembert's ratio test. If the same function having the powers of n, so if the function having powers of n like 1 by 2 whole power n, 1 by n whole power n, so like that problems is there means directly we can apply the Cauchy's root test. So in the next lectures and all, I'm going to discuss briefly about Cauchy's root test and D'Alembert's ratio test, and also few examples related to the Cauchy's root test and D'Alembert's ratio test. Thank you.